If you've ever felt like space keeps its biggest secrets just out of reach, subscribe right now, because what James Webb just saw wasn't supposed to exist. And once you hear this, you won't see the universe the same way again. The deeper James Webb looks, the more our old story about how the universe grew starts to fall apart. And tonight, I'm going to show you why scientists at NASA and some of the world's top observatories are quietly rethinking the timeline of everything. For most of human history, we looked up and saw dots of light. With Hubble, we started to see shapes. With James Webb, we are seeing the universe as it was when it was still learning how to breathe. Webb is sitting far beyond the moon, near a point called L2, quietly collecting light that started its journey before Earth even existed. Teams at NASA Jet Propulsion Laboratory guide it. Scientists from the Harvard-Smithsonian Center for Astrophysics help decode what it sends back. Researchers working with the European Southern Observatory compare Webb's infrared data with what ground telescopes, like the Very Large Telescope, can see from Chile. And every time Webb opens its eye, something strange shows up. The plan was simple. Look deep into space. Find the first tiny galaxies. Watch how the universe slowly grew from simple clouds of gas into stars, then into small galaxies, then into bigger ones. That's the story written in textbooks. That's the story taught in schools. The early universe was supposed to be messy, slow, and simple. But Webb isn't seeing simple. It's seeing big, bright, heavy galaxies where there should barely be anything at all. Some of the galaxies Webb has found look fully grown when the universe was only a few 100 million years old. That's not enough time, according to our best models, for that much matter to gather, cool down, form stars, and build structure. Scientists working with Hubble spectrograph records expected to see faint smudges at that age. Instead, Webb shows bright islands of stars, packed tight, already shaped into disks and clusters. It's like showing up at a construction site where the ground was cleared yesterday and finding a finished city today. People at Caltech and the Harvard-Smithsonian Center for Astrophysics started double-checking the data. Could the distances be wrong? Could the galaxies be closer than they look? Teams compared Webb's infrared readings with older Hubble data and with ground-based measurements from Keck Observatory in Hawaii. The redshifts line up. The distances check out. These galaxies are really that far, and that means they really are that old, or young, depending on how you look at time. Either way, the math doesn't like it. This puts scientists in a tough spot. Either the universe formed big galaxies much faster than we thought, or something about our understanding of early cosmic growth is missing. The first option means gravity, gas cooling, and star formation were far more efficient in the early universe than our models predict. The second option is even scarier. It means some of the rules we use to explain how structure forms in the universe might be incomplete. At the European Southern Observatory, researchers compared Webb's galaxy data with simulations used to model dark matter halos, the invisible scaffolding that galaxies grow on. The halos in the simulations are too small and too slow to explain what Webb is seeing. At NASA JPL, scientists looked at how quickly gas could fall into these early halos and form stars. Even with generous assumptions, the numbers struggle to match the brightness Webb is recording. Something isn't lining up, and when physics stops lining up, scientists get nervous. This isn't the first time the universe has done this to us. In the 1990s, when astronomers using data connected to Arecibo, legacy data, and other radio surveys studied galaxy motion, they found galaxies spinning too fast for the visible matter they had. That led to dark matter. Later, distant supernova observations suggested the universe's expansion was speeding up, leading to dark energy. Each time, the universe shrugged at our neat ideas and forced us to add something new to the story. Webb might be doing that again. And it's not just galaxies. Webb has started to look at the chemistry of early stars and star-forming regions. Using its infrared instruments, scientists can see molecules forming in dust clouds billions of years ago. Water vapor, carbon compounds. The building blocks of complex chemistry were already floating around very early in cosmic history. That raises another uncomfortable question. If the ingredients for life were around so early, how common might life-friendly chemistry be across the universe? Not life itself, just the raw materials. Even that changes how we think about how special our corner of space is. Meanwhile, teams studying Voyager 1 telemetry data remind us how strange our own space neighborhood can be. Voyager is still sending back whispers from beyond the edge of the sun's influence, showing us that even the space between stars is full of structure and energy. Combine that with Webb's view of the early universe, and the picture starts to feel less like a calm ocean and more like a busy highway of matter, radiation, and change. But here's where the tension really kicks in. Some of the galaxies Webb sees look too heavy for their age. Their starlight suggests they already turned a lot of gas into stars. That means star formation in the early universe might have been faster, hotter, and more intense than anything we see today. The universe might have gone through a wild growth spurt, like a child who suddenly shoots up overnight. If that's true, then our timeline of cosmic history needs a rewrite. Scientists are careful with words. You won't hear them say the universe is broken. What you'll hear is our models may need refinement, but between the lines, you can feel the discomfort. When data from James Webb Space Telescope checked against Hubble spectrograph records, Keck Observatory measurements, and simulations used at institutions like Stanford refuses to behave, it means something important is missing from the picture. So the problem is simple to state and hard to solve. The early universe is not supposed to look this mature. The galaxies are too big, too bright, too organized. Either nature moved faster back then, or our understanding of nature is incomplete. And when your understanding of nature is incomplete, every other conclusion built on it starts to wobble. That's where things get interesting. Because if the early universe grew differently than we thought, it changes how we think about everything that came after. How fast stars formed, how early black holes grew, how quickly planets could exist, how soon complex chemistry could spread through space. It's like pulling one brick from the bottom of a wall and watching the cracks race upward. In the next part, we're going to follow how scientists are trying to fix this puzzle, the new ideas they're testing, and why some of them are controversial even among experts who spent their whole lives studying the cosmos. As the shock from those early James Webb images settled in, the next step for scientists wasn't panic. It was detective work. When something in the universe doesn't match the story we tell about it, the first rule is simple. Check everything twice. Then, check it again. Teams at NASA Jet Propulsion Laboratory went back to the raw data. They reran the calibration. They compared Webb's infrared readings with older Hubble spectrograph records. They asked colleagues at the European Southern Observatory to cross-check the same regions of sky using different instruments. If there was a mistake hiding in the numbers, someone was going to find it. But the more they checked, the more solid the results became. The galaxies were real. Their distances were real. Their brightness was real. That meant the problem wasn't in the telescope. The problem was in our expectations. So scientists started asking a different question. What if the early universe was better at building galaxies than we thought? The models we use today are based on how galaxies form now, in a calmer, older universe. Back then, space was denser. Gas clouds were closer together. Dark matter halos were still forming and crashing into each other. It might have been a chaotic time where everything happened faster. Researchers at the Harvard-Smithsonian Center for Astrophysics ran new simulations where gas cooled more quickly and star formation kicked off earlier. Those models got closer to Webb's data, but they still struggled to explain how some galaxies got so big, so fast. Another idea started to gain attention. What if the first stars were different? Today, most stars are born small and slow. But some astronomers believe the first generation of stars, called population 3 stars, were massive and short-lived. They would have burned hot and died young, flooding their galaxies with heavy elements and energy. That could speed up galaxy growth. Teams using data from Keck Observatory in Hawaii began searching for chemical fingerprints in Webb's galaxy spectra that might hint at these early monster stars. The signs are subtle, but some results suggest early star formation was far more intense than what we see around us today. Then there's the black hole problem. Webb is finding young galaxies that already seem to host massive black holes at their centers. According to our old timeline, black holes shouldn't have had enough time to grow that large. Yet here they are, sitting in the hearts of galaxies that are barely toddlers in cosmic terms. Astronomers working with colleagues at Stanford and using models inspired by Ronald Bracewell's old ideas about advanced detection methods are trying to understand how these black holes could grow so fast. Did they start bigger than we thought? Did they feed more aggressively on surrounding gas? Or is there a piece of physics about gravity and collapse that we haven't fully grasped yet? As these questions stack up, another tension appears. If galaxies and black holes formed earlier and faster, then the timeline for planet formation might also shift. That doesn't mean life existed back then. It just means the universe became chemically rich much sooner. Water, carbon, and oxygen didn't wait around. They spread early. Data from the James Webb Space Telescope shows complex molecules in regions of space that formed not long after the first stars ignited. This doesn't tell us there was life. It tells us the kitchen had ingredients long before we thought the stove was even turned on. This also changes how scientists think about dark matter. The scaffolding that galaxies grow on might behave differently in the early universe. Teams working with simulations tied to Vera Rubin Observatory's upcoming sky surveys are preparing to test whether dark matter clumped more tightly in the past. If it did, that would help explain how galaxies could grow big so quickly. Vera Rubin Observatory isn't fully online yet, but when it is, it will scan the sky again and again, catching faint movements and changes that older surveys missed. That will give scientists a wider view of how matter moves through space over time. But here's where the challenge becomes more than technical. These discoveries don't just tweak numbers in a model, they mess with the story we tell ourselves about our place in the universe. We like to think of the early cosmos as simple and empty, slowly building toward complexity. Webb is showing a universe that grew up fast, full of light and structure, almost right away. That makes our cosmic story feel less like a slow climb and more like a sudden sprint. Some scientists push back hard against rewriting the timeline. They argue that we're still at the beginning of Webb's mission and that early data can be misleading. That's fair. New tools often surprise us at first, and the full picture takes time. But even the cautious voices admit that something important is happening. When independent teams at NASA, JPL, the European Southern Observatory, and the Harvard-Smithsonian Center for Astrophysics all see the same strange pattern, it's not noise. It's a signal that our map of the universe has missing roads. And there's another layer to this. When Webb looks deep into space, it's also looking deep into time. Every strange galaxy is a message from a past we thought we understood. It's like reading an old diary and realizing the writer lived a much wilder life than you imagined. The universe is telling us it grew up fast, broke some of our rules, and then settled into the calmer rhythm we see today. One scientist accepted that the early universe might have grown up faster and wilder than we imagined. A much bigger question landed on the table. If our timeline for galaxy growth is off, what else might be off? Because the story of the universe isn't just about stars and galaxies. It's about how space itself stretches, how fast everything is moving apart, and where this whole thing is headed in the long run. For years, astronomers have relied on a simple picture. The universe is expanding, and that expansion is speeding up because of something we call dark energy. We don't know what dark energy is, but we measure its effects. Teams using Hubble spectrograph records and data from supernova surveys mapped how fast galaxies are moving away from us. Then along came James Webb, peering much deeper and much earlier, and suddenly some of those measurements don't line up as neatly as before. Here's the problem in plain words. When scientists measure the expansion rate of the universe using nearby objects, they get one number. When they measure it using very distant, very early objects, they get another. This is known as the Hubble tension. It's been a headache for cosmologists for years. Webb's deep field data is now adding fuel to that headache. Some of the early galaxies it sees appear brighter and more massive than expected, which can mess with distance estimates. If distances are off, then expansion rates might be off too. Researchers at NASA Jet Propulsion Laboratory and the Harvard-Smithsonian Center for Astrophysics have started rerunning the math using Webb's new galaxy samples. They're testing whether the early universe might have gone through phases of faster or slower expansion than our models assume. If that's true, then dark energy might not be constant. It might change over time. That's a big deal, because most current theories treat dark energy as a steady push that never changes its strength. The European Southern Observatory has also been feeding Webb's discoveries into its models of large-scale structure. When galaxies form earlier, the web of matter that connects them, the cosmic web, also forms earlier. That changes how gravity shapes the universe on the biggest scales. Even small tweaks to these models can lead to very different futures for the cosmos. In one version, expansion keeps speeding up forever, and everything drifts apart into cold darkness. In another, expansion slows down slightly, changing how galaxies cluster billions of years from now. We're not talking about small details. We're talking about different endings to the story of everything. There's also the question of how reliable our cosmic yardsticks are. Astronomers use certain stars and explosions as distance markers, things like Cepheid variables and supernovae. But Webb is seeing star populations in early galaxies that don't look like anything we see nearby. That raises a simple but scary possibility. What if some of our distance tools only work well in the modern universe, not in the early one? If that's the case, then parts of our cosmic map might be drawn with the wrong scale. Teams are now trying to anchor Webb's deep observations to older data from Voyager 1 telemetry, which gives us a clean picture of the local space environment, and from Arecibo legacy data, which map distant objects in radio waves before the telescope went quiet. By stitching together local and distant measurements, scientists hope to tighten the scale of the universe and reduce these mismatches. It's slow work. Every small error compounds over billions of light years. While all this is happening, another idea is quietly gaining attention. What if the universe isn't as smooth and uniform in its growth as we thought? What if different regions evolved at slightly different speeds early on? That could explain why some patches of the early universe look more mature than others. Data from Keck Observatory and upcoming wide surveys from Vera Rubin Observatory will help test this by mapping huge swaths of sky for patterns in galaxy ages and structures. If there are large-scale differences, that would mean the early universe had more personality than our simple models allow. And here's the emotional part of this story. For decades, students were taught a neat timeline. First, darkness, then small stars, then small galaxies, then bigger ones. Webb is tearing that timeline apart and saying the universe may have been more like a fireworks show from the start, bright, crowded, and busy right out of the gate. That doesn't mean the old scientists were wrong. They worked with the best tools they had. But it does mean that every generation of scientists is, in a way, rewriting the universe for the next one. The deeper Webb looks, the more it forces us to admit something uncomfortable. We don't just need new answers. We may need new questions. Not, why did galaxies form so early? But what rules did the early universe actually play by? And if those rules were different, then the story of how everything began, from stars to planets to the ingredients of life, might be far stranger and richer than the calm story we've been telling ourselves. Now let's bring the story closer to home, because James Webb isn't just rewriting how the early universe formed. It's also changing what we think about planets, atmospheres, and the chances of life beyond Earth. This is where things stop being abstract and start to feel personal. When we talk about distant galaxies, it's amazing, sure. But when we talk about worlds that could carry water, air, maybe even life, that hits differently. Before Webb, most of what we knew about exoplanets came from indirect methods. We saw tiny dips in starlight when a planet passed in front of its star. We could guess a planet's size, its orbit, and maybe whether it was rocky or gassy. But guessing isn't knowing. Webb changed that by letting us read the light that passes through a planet's atmosphere. It's like holding a glass up to the sun and seeing what color the glass is. That color tells you what the glass is made of. Webb does the same thing, but with entire alien worlds. Teams working with NASA, Jet Propulsion Laboratory, and the European Southern Observatory started pointing Webb at hot gas giants first, because they're easier targets. And what came back was wild. Webb detected clear signatures of water vapor, carbon dioxide, and methane in several exoplanet atmospheres. That alone is huge. But then came the weird part. Some planets showed chemical mixes that shouldn't be stable under their star's radiation. The ratios were off. Either our models of atmospheric chemistry are missing something, or these atmospheres are being constantly reshaped by processes we don't fully understand yet. Then Webb turned its eyes to smaller, cooler planets, including a few in the so-called habitable zones of their stars, places where liquid water could exist. In systems like TRAPPIST-1, Webb started to rule out thick hydrogen atmospheres on some of the inner planets. That sounds boring, but it's actually exciting. Thick hydrogen blankets would make life as we know it unlikely. Thinner atmospheres, more like Earth's, keep the door open. It doesn't mean there's life there. It means the door isn't slammed shut. Scientists at the Harvard-Smithsonian Center for Astrophysics and Keck Observatory have been pairing Webb's data with ground-based measurements to build full climate models of these worlds. They're asking simple questions with huge weight. Does this planet hold on to heat? Does it lose its atmosphere to stellar storms? Does it have clouds that reflect light and cool the surface? Every answer changes how common life-friendly worlds might be in the galaxy. And then there's the hunt for biosignatures. These are chemical hints that, on Earth, are linked to life, things like oxygen alongside methane. The tricky part is that nature can fake these signals. Volcanoes, sunlight, and chemistry can produce similar mixes. Webb isn't shouting life found. It's whispering, this planet is interesting. Look closer. That whisper is enough to shift how future missions are planned. Suddenly, target lists are being rewritten. Worlds that once looked boring are getting promoted to must-watch status. What's also changing is how we think about the building blocks of life in space. Webb has been detecting complex organic molecules in star-forming regions, the raw stuff that can later become part of planets. Observations from ESO and comparisons with Arecibo legacy data in radio wavelengths show that these molecules are more common and more widespread than we once thought. The universe seems to be good at making the ingredients for life. The big unknown is how often those ingredients actually cook into something alive. There's a quiet shift happening in astrobiology because of this. Instead of asking, is life rare? Scientists are starting to ask, is life common but short-lived? If planets form quickly, atmospheres change fast, and stars can be violent when young, then windows for life might open and close like doors in a hallway. Webb is giving us snapshots of many doors at different stages. Some open, some slam shut, some halfway there. Voyager 1 telemetry reminds us of another piece of this puzzle. Out beyond the edge of the solar system, we can measure the local interstellar environment. The conditions out there shape how radiation and particles flow into our system. That same kind of environment exists around other stars. Webb's exoplanet data, combined with what Voyager tells us about our own cosmic neighborhood, helps scientists understand how harsh or gentle these stellar neighborhoods really are. Some stars may cook their planets, others might cradle them. All of this leads to a strange feeling. The more Webb shows us, the less special Earth seems in terms of ingredients. Water, carbon compounds, rocky worlds, they're everywhere. But at the same time, Earth starts to look special in timing and balance. We might be living in a narrow window where everything lined up just right for long enough that doesn't make us lonely in the universe. It makes us lucky. Let's zoom out even more, because once you start seeing planets and galaxies differently, you can't avoid the deeper question. What's actually holding this whole thing together? For a long time, astronomers have known that most of the universe is invisible, not hidden behind dust, literally invisible. Galaxies spin too fast. Clusters of galaxies hold together when they shouldn't. Something with mass is there, shaping gravity, but it doesn't glow, it doesn't reflect light, and it doesn't behave like normal matter. We call it dark matter because we don't know what else to call it. Before James Webb, dark matter was mapped mostly through indirect methods, like watching how galaxies bend light from objects behind them. Gravitational lensing showed us the outline of these invisible structures, like seeing the shape of a ghost by how it pushes on fog. Webb added a new layer to this story. By seeing faint galaxies in the early universe, with more detail than ever before, Webb lets scientists trace how matter clumped together just a few 100 million years after the Big Bang. Teams working with data from the Vera Rubin Observatory and simulations from NASA Jet Propulsion Laboratory have started to notice something odd. The way early galaxies form and group together seems faster and more organized than some models predicted. It's as if the scaffolding of dark matter was already in place, guiding matter into shape earlier than expected. Think of it like building a city. You expect roads and power lines to come after people move in. But Webb's view of the early universe looks more like the roads were laid down first, and the buildings followed almost immediately. This suggests that dark matter structures formed very early and acted like invisible highways, pulling gas and dust into growing galaxies. The timing is tighter than our old models allowed. There's another strange detail. Webb is sensitive to infrared light, which means it can peer through cosmic dust clouds that hide young galaxies from optical telescopes. When astronomers at ESO and Keck Observatory compared Webb's deep field images with Hubble spectrograph records, they found entire populations of galaxies that were previously undercounted. These hidden galaxies change the math. If there are more early galaxies than we thought, then the role of dark matter in shaping them has to be even more efficient. Something about the early universe was very good at organizing chaos. This has ripple effects for how we think about dark energy too, the mysterious force driving the universe to expand faster over time. The growth of early galaxies sets limits on how strong dark energy could have been in the past. If dark energy had been too strong early on, matter wouldn't have clumped together so quickly. Webb's data hints that dark energy's influence might have changed over time, or at least that our simple models don't capture the full story. It's not that dark energy is suddenly wrong, it's that the universe may be more complicated than our clean equations suggest. Then there's the cosmic web, the vast network of filaments made of dark matter and gas that connects galaxy clusters across billions of light years. Webb can't see dark matter directly, but it can see where galaxies line up along these filaments. The pattern is eerily neat. Clusters form at the intersections of these filaments, like knots in a net. Researchers at Harvard-Smithsonian Center for Astrophysics have been using Webb's data to refine maps of this web at earlier times than ever before. The result is a picture of a universe that looks structured very early, not a slow, messy build, but a fast one with clear patterns from the start. Here's where it gets uncomfortable in a good way. If the universe organized itself this quickly, then either our understanding of gravity on large scales is incomplete, or dark matter behaves in ways we don't yet grasp. Some scientists have even revisited old ideas about modified gravity, not because dark matter is being abandoned, but because the data is forcing them to test every assumption. It's the same process that happened with a pioneer anomaly decades ago. For years, something didn't add up with spacecraft motion. Eventually, the explanation turned out to be heat from the craft itself. The lesson stuck. Weird data doesn't mean new physics every time, but it always means check everything. What Webb is doing is giving us enough precision that our mistakes become obvious. Old shortcuts in models don't hide anymore. When the universe doesn't behave the way your math says it should, you have two choices. You fix the math, or you admit you're missing a piece of the universe. Now, let's talk about the stars themselves, because the way the first stars lit up the universe is turning out to be way less simple than the old story we were taught. For a long time, astronomers believed the first stars, called population 3 stars, were massive, short-lived, and rare. These were the very first furnaces in the universe, born from pure hydrogen and helium left over from the Big Bang. No carbon, no oxygen, no iron, just simple gas collapsing under gravity. According to models built from data at places like NASA, Jet Propulsion Laboratory, and the Harvard-Smithsonian Center for Astrophysics, these stars should have been huge, bright, and brief. They burned hot, lived fast, and exploded as supernovae, seeding the universe with the first heavy element. The problem is, Webb is finding evidence that star formation in the early universe may have been happening faster and in more complex ways than those models expected. When Webb looks at galaxies that existed only a few 100 million years after the Big Bang, it sees signs of surprisingly mature stellar populations. Not just a few giant stars burning themselves out, but groups of stars forming in clusters, lighting up their host galaxies with patterns that look more organized than chaotic. This matters because stars are the factories that build everything heavier than hydrogen and helium. Carbon in your body, oxygen you breathe, iron in your blood, all of that was made in stars that lived and died before the sun was born. If early stars formed faster and in larger numbers, then heavy elements spread through the universe earlier too. That speeds up the timeline for planets, atmospheres, and maybe even the raw materials for life to appear. Spectroscopy from Webb, cross-checked with data from Keck Observatory and old Hubble spectrograph records, shows early galaxies with more dust and metal content than expected. Dust is made from heavy elements, and heavy elements come from multiple generations of stars. This suggests that by the time the universe was only a few 100 million years old, some regions had already gone through cycles of star birth and death. That's like finding smoke from a campfire in a place you thought no one had lit a match yet. There's also the question of how these first stars shaped their surroundings. When massive stars ignite, they flood space with ultraviolet light. That light strips electrons from hydrogen atoms, turning neutral gas into ionized plasma. This period, called the epoch of reionization, marks the moment the universe went from dark and foggy to transparent. Webb's observations, combined with radio data connected to Arecibo legacy surveys and models from the Vera Rubin Observatory teams, suggest reionization may have been patchy and uneven. Some regions cleared early, others lagged behind. The early universe may have looked like a night sky where lights turned on in pockets, not all at once. This uneven lighting has consequences. In regions that lit up early, gas was heated and blown around, sometimes slowing later star formation. In darker pockets, gas could quietly collapse into new stars for longer. The result is a universe with neighborhoods that matured at different speeds. Some areas rushed into complexity, others took their time. That uneven start could explain why we see such a wide range of galaxy shapes and sizes today. Another twist comes from how these early stars may have lived and died. Some models predict that the first stars were so massive that they collapsed directly into black holes without big explosions. If that happened often, it could help explain why Webb is finding surprisingly massive black holes at very early times. Observations from Webb and ESO hint at black holes in the centers of young galaxies that are far heavier than we expected them to be so soon after the Big Bang. That means either black holes grew insanely fast or they were born big to begin with. Either way, the early universe looks less like a slow, gentle start and more like a fast, crowded rush. Stars formed quickly, black holes appeared early, heavy elements spread faster than expected. The building blocks of complexity were in place much sooner than our neat timelines predicted. And here's the uncomfortable thought. If the raw materials for planets and life spread early, then the window for life elsewhere in the universe may have opened much earlier than we thought. Life, at least in simple forms, may not be a late arrival in cosmic history. It could be woven into the story almost from the beginning. For decades, astronomers believed black holes grew slowly. You start with the corpse of a massive star, maybe 10 or 20 times the mass of our Sunday. Over millions of years, that black hole feeds on gas, dust, and sometimes other stars. Given enough time, it can grow into a monster with millions or billions of times the mass of the Sunday. That story fits what we see in the nearby universe, but it completely falls apart when we look at the early universe with the James Webb Space Telescope. Webb is finding galaxies that existed when the universe was only a few 100 million years old, and at their centers are black holes that are already enormous. Some appear to be tens of millions, even hundreds of millions of solar masses. According to standard growth models used by teams at NASA Jet Propulsion Laboratory and the Harvard-Smithsonian Center for Astrophysics, there simply wasn't enough time for black holes to grow that big through slow feeding. It's like finding a full-grown adult where you expected to see a baby. So scientists are now considering ideas that used to sit at the edge of mainstream thinking. One possibility is direct collapse black holes. Instead of forming from dead stars, huge clouds of gas might collapse straight into black holes, skipping the star phase altogether. This could create black holes that start life already thousands or even hundreds of thousands of times the mass of the Sunday. Observations from ESO and modeling work linked to Keck Observatory support the idea that in the dense, hot, early universe, conditions may have allowed for this kind of fast-track black hole birth. Another idea is super Eddington growth, There's a theoretical limit to how fast a black hole can eat before the light and energy it produces push material away. But some models suggest that early black holes could have fed in messy, chaotic ways that let them grow faster than this limit, at least for short periods. Webb's data on bright, compact galaxies hint that intense feeding frenzies might have been common in the early universe. There's also the role of mergers. In the young universe, galaxies were packed closer together. Collisions and mergers were common. When galaxies merge, their central black holes eventually spiral together and merge too. Each merger makes a bigger black hole. Webb is catching galaxies in what look like early stages of these violent dances. And that could help explain how black holes gain mass so quickly. What makes this more unsettling is how these early black holes shape everything around them. When a black hole feeds, it doesn't do it quietly. It blasts out energy in jets and radiation that can heat nearby gas, shut down star formation, or sometimes trigger new stars to form in shock waves. So these early black holes may have acted like cosmic architects, carving out the structure of their host galaxies from the inside out. Data from Webb, paired with older Hubble spectrograph records, show galaxies whose light is dominated by active cores, suggesting black holes were already powerful players very early on. This flips our old picture. We used to think galaxies formed first and black holes grew later inside them. Now it's starting to look like black holes may have grown alongside galaxies or even helped shape them from the very beginning. It's less like galaxies built houses for black holes and more like black holes moved in early and started remodeling the whole place. And that leads to a deeper question. If black holes were already big and active so early, what does that mean for the stability of early galaxies? How did stars manage to form at all in environments flooded with radiation from hungry black holes? The fact that we see mature galaxies alongside these monsters suggests the early universe found ways to balance chaos and creation at the same time. Let's pull the camera back even more, because what Webb is showing us isn't just a few weird objects. It's a pattern. And patterns are what make scientists nervous, because they're harder to explain away as flukes. For years, our best model of how the universe grows and evolves has been called lambda CDM. It's the framework used by teams at NASA Jet Propulsion Laboratory, the European Southern Observatory, and pretty much every major cosmology group at places like the Harvard-Smithsonian Center for Astrophysics. In simple terms, it says the universe starts smooth after the Big Bang. Tiny ripples grow under gravity. Dark matter forms the scaffolding. Gas falls in. Stars form, and galaxies slowly build up over time. It's a calm, gradual story of growth from small to big. Webb is not seeing calm or gradual. It's seeing big, organized structures way too early. We're finding galaxies with disks, bulges, and clear shapes when the universe was still in what should have been its messy childhood. Some of these galaxies already look like grown adults, when, by the old timeline, they should still be awkward teenagers. Researchers comparing Webb data with predictions from Vera Rubin Observatory simulations are noticing the same tension. The simulations make galaxies that are too small and too simple compared to what Webb is actually observing. This doesn't mean the whole model is wrong, but it does mean something important is missing. One missing piece could be how fast gas cooled and formed stars in the early universe. If gas cooled faster than we thought, galaxies could have built up their mass much more quickly. Another missing piece could be how dark matter behaves on small scales. If dark matter clumps more tightly or forms dense seeds earlier than our models predict, it would give normal matter a head start in building large galaxies. There's also the question of feedback. In our models, early star formation and black hole activity blow out gas and slow down growth. But Webb is showing galaxies that seem to have powered through that phase without slowing down much. That suggests feedback might be less effective in the early universe, or that gas was pouring in so fast that even powerful outflows couldn't stop growth. Observations of gas flows around early galaxies, studied using Webb's infrared instruments and follow-ups from Keck Observatory, hint at streams of fresh material feeding young galaxies like open taps. Another layer to this story is dust. We used to think early galaxies would be almost dust-free, because dust forms in the aftermath of many generations of stars. But Webb is detecting dust in surprisingly young galaxies. Dust changes how galaxies cool, how stars form, and how light escapes. If dust formed faster than expected, it could help explain why early galaxies look more mature and structured than our models predicted. When you stack all of this together, it starts to look like the early universe was a much more intense place than we imagined. Faster star formation, faster black hole growth, faster buildup of structure. The universe may have had a kind of growth spurt, a wild early phase where everything happened at breakneck speed, before settling into the slower pace we see today. And here's the uncomfortable part. If our models are missing key physics about how fast structure can form, then our estimates of how old some cosmic structures are might be off. That doesn't mean the age of the universe itself is wrong, but it does mean our picture of its childhood could be incomplete. It's like finding baby photos of the universe where the kid already looks like a teenager. Something in the story of how it grew up needs rewriting. Now let's step into even deeper water, because once you admit the early universe grew up too fast, you're forced to ask a dangerous question. What if the beginning wasn't as smooth and simple as we've been telling ourselves? For decades, data from the cosmic microwave background, mapped in detail by missions like Planck, and analyzed by teams linked to NASA, JPL, and the European Space Agency, showed the early universe as almost perfectly even. Tiny temperature ripples, 1 part in 100,000. Those ripples were supposed to be the seeds of everything we see today. Small seeds, slow growth, simple start. Webb is hinting that those seeds might not have been so small after all. When astronomers combine Webb's galaxy counts with deep field data from Hubble spectrograph records and newer surveys planned with the Vera Rubin Observatory, something odd shows up. The number of massive galaxies at very early times seems higher than what smooth, tiny ripples would produce. That points to the possibility that some regions of the early universe were already more lumpy than our current models allow. In plain words, the universe might have had built-in hotspots, areas primed to grow big structures fast. One way to explain this is to tweak inflation, the brief, violent expansion that happened right after the Big Bang. Inflation is supposed to stretch tiny quantum bumps into the seeds of galaxies. But what if inflation wasn't uniform? What if some patches expanded a bit differently, leaving behind stronger seeds in certain regions? That would create pockets of the universe where galaxies formed fast and grew big early, while other regions stayed quiet longer. Another idea on the table is that there could be extra physics in the dark sector. Dark matter and dark energy make up most of the universe, but we barely understand them. Researchers at places like Stanford, building on early ideas about exotic physics beyond standard models, are exploring whether dark matter might interact with itself or with normal matter in subtle ways. If dark matter could clump faster in the early universe, it would give galaxies a head start. That would neatly explain why Webb sees mature galaxies when it shouldn't. There's also the role of early black holes. Webb and follow-up observations from the Keck Observatory have found signs of surprisingly massive black holes sitting in young galaxies. Black holes grow by feeding on gas, but gas also falls into galaxies along the same filaments of dark matter. If black holes formed earlier and grew faster than we thought, they could act like anchors, helping galaxies pull in more material and bulk up quickly. The Harvard-Smithsonian Center for Astrophysics has teams actively modeling how early black holes could reshape galaxy growth timelines. And those models are starting to look less crazy than they did a few years ago. All of this pushes us toward an uncomfortable picture. The early universe might not have been one clean, simple starting line for everyone. It might have been more like a chaotic race, with some regions getting a massive head start. That breaks the cozy idea that everything began evenly and evolved slowly under the same rules everywhere. And once you accept that, another question pops up. If the early universe had built-in differences from the start, how much of what we see today is the result of those early advantages? Are we living in a region that just happened to be lucky at birth, in a part of the universe that got a head start on building stars, galaxies, and eventually planets like ours? The deeper Webb looks, the more it hints that our cosmic origin story might not be as fair or as simple as we once believed. Here's where the report gets even stranger. Because once you accept that the early universe may have had built-in hotspots, you have to face what that means for everything that came after, including us. Astronomers use giant computer simulations to replay the birth of the universe. These simulations run on supercomputers and guided by data from NASA, JPL, the European Southern Observatory, and long-term Hubble Deep Field surveys start with those tiny ripples in the early universe and let gravity do the rest. Over billions of years, matter flows along invisible filaments, galaxies grow, clusters form, and the large-scale web of the cosmos appears. But when researchers plug Webb's new galaxy counts into these simulations, the numbers don't line up. To get that many big galaxies so early, they have to cheat the starting conditions. They either boost the amount of matter in certain regions, change how fast gas cools, or allow black holes to form and grow much earlier than current theory says they should. In other words, the universe we are seeing doesn't want to grow according to the old rules. This is forcing scientists to rethink something very basic: how fast structure can form. The classic picture says gravity is slow. You start with tiny clumps, and over hundreds of millions of years, they slowly pull more matter in. Webb's data suggests that in some places, gravity may have had help. Not magic help, but help from physics we don't fully understand yet. Maybe dark matter interacts in ways we haven't measured. Maybe early stars were far more efficient at forming and recycling material than we thought. Maybe there were exotic processes in the young universe that only happened once and never again. Teams using the James Webb Space Telescope are now working closely with observers at the Keck Observatory in Hawaii and analysts using Arecibo legacy data to cross-check these early findings. Even though Arecibo is no longer operating, its long record of radio observations helps set limits on how much unseen matter could be hiding in certain regions of space. When all these pieces are combined, the picture that forms is unsettling. The early universe might have been more dynamic, more uneven, and more aggressive in building structure than our neat equations predicted. And here's the quiet twist that doesn't get talked about enough. If the universe builds galaxies faster in some places, that also means it builds the conditions for planets and life faster in some places. Heavy elements like carbon, oxygen, and iron are made inside stars and spread by explosions. If stars formed earlier and faster in certain regions, those regions could have become life-friendly far sooner than others. The Harvard-Smithsonian Center for Astrophysics has pointed out that early star formation changes the timeline for when planets like Earth could even exist. So the Webb results don't just mess with timelines of galaxies, they mess with timelines of habitability. It raises a wild but serious question. Could there be parts of the universe where life had a head start of hundreds of millions, maybe even billions of years over us? That thought alone is enough to make you sit back and stare at the ceiling for a moment. Now let's talk about something even more uncomfortable for scientists: the numbers themselves. When astronomers count galaxies in Webb's deepest images, they're not just seeing a few extra. In some early universe fields, they're seeing several times more massive galaxies than the models predicted. This isn't a small error you can fix by tweaking one setting. It's the kind of gap that usually means your starting idea is missing something big. Researchers working with data pipelines at NASA's Jet Propulsion Laboratory and teams coordinating with the Vera Rubin Observatory have been double-checking these counts with different methods. They change how they estimate distance. They change how they correct for dust. They test different assumptions about how bright early stars should be. And still, the same story keeps showing up. The universe had no business building so many big galaxies so early, but it clearly did. One possible explanation people are exploring is that the first stars were not like the stars we see today. The very first generation, often called population 3 stars, may have been massive monsters, hundreds of times heavier than our sun, burning bright and dying fast. If that's true, they could have pumped huge amounts of energy and heavy elements into their surroundings in a short time, jump-starting galaxy growth. The problem is, we've never directly seen these stars. We only infer them from theory and from faint chemical clues in later galaxies. Another idea is that black holes formed much earlier and grew much faster than we thought. Webb has already spotted surprisingly massive black holes in very young galaxies. To get that big so fast, black holes would have to feed almost non-stop, pulling in gas at near the maximum rate allowed by physics. Teams using Webb's infrared spectra and follow-up measurements from the European Southern Observatory are now trying to measure how these early black holes behave, because they may be the engines that powered these early galaxies into maturity. And then there's dark matter, the invisible stuff that makes up most of the universe's mass. Our models treat dark matter as cold and quiet, just sitting there and letting gravity do its slow work. But what if dark matter is not so passive? What if, in the early universe, it clumped faster, interacted weakly with itself, or created deeper gravitational wells than we assumed? Small changes in dark matter behavior could speed up the whole process of galaxy formation without breaking any known laws of physics, just by adding a new chapter to them. All of this points to the same uncomfortable truth. Webb isn't just adding details to our picture of the universe. It's poking holes in the foundation. The early universe looks less like a slow, gentle nursery and more like a chaotic construction site where massive structures went up in a rush. And the deeper Webb looks, the more this pattern shows up. Here's where it gets even stranger. Because Webb isn't just changing how we think galaxies formed, it's also changing how we think galaxies grow and age. When astronomers at the Harvard-Smithsonian Center for Astrophysics compare Webb's early galaxy images with what Hubble saw in slightly later eras, they expected to see a clear story. Small, messy galaxies slowly merging and settling into the neat spirals and ellipticals we see today. Instead, Webb is showing galaxies that already look surprisingly organized very early on. Some have disc-like shapes, some show signs of ordered rotation. That kind of structure usually takes time to develop, like a city planning its streets after decades of growth. But these cosmic cities seem to have zoning laws almost from day one. To test whether these shapes are real or just illusions caused by distance and dust, teams are using spectroscopy from the Keck Observatory in Hawaii. By measuring how gas moves inside these galaxies, they can tell whether the structure is truly rotating or just looks that way because of how light bends across space. Early results suggest that, yes, at least some of these galaxies are already rotating in a fairly stable way. That's a big deal. It means the early universe wasn't just chaotic lumps crashing together. There was order emerging much sooner than expected. This forces scientists to rethink how fast cosmic weather settles down. In our models, gas clouds collide, stars explode, black holes flare up, and everything is messy for a long time before a galaxy calms into a steady shape. But Webb's data hints that nature may be better at organizing chaos than we gave it credit for. Gravity might be a faster architect than we assumed. Another surprise is how dusty these early galaxies appear. Dust forms when stars live and die, especially when massive stars explode as supernovae. Seeing a lot of dust early on means stars were forming, living, and dying in huge numbers very quickly. That lines up with the idea of early, massive stars. But again, it compresses timelines that we thought were much longer. It's like finding soot in a fireplace you thought was just built yesterday. This also affects how we measure distances and ages. Dust can hide stars and change how bright a galaxy looks, which means some of our old estimates might be off. Teams using data from the James Webb Space Telescope, combined with older Hubble spectrograph records, are now rechecking ages of early galaxies. Some objects, once thought to be slightly younger, may actually be even closer to the dawn of time than we believed. So every time scientists think they've pinned down the early universe, Webb nudges the story sideways. The universe didn't politely follow our timelines. It sprinted ahead, built big things fast, and then left us to catch up and explain how it pulled off that trick. And just when you think the story can't get any more surprising, Webb starts poking holes in one of the biggest ideas we use to explain the universe at all: how fast it's expanding. For years, astronomers have been arguing about something called the Hubble tension. In simple terms, different methods of measuring how fast the universe is growing give different answers. One set of measurements, based on nearby galaxies and supernovae, suggests the universe is expanding faster. Another set, based on the ancient light from the Big Bang, suggests it's expanding slower. It's like timing the same runner with two stopwatches and getting two different times. Someone is wrong, or the rules of the race aren't what we think they are. Webb stepped into this argument with sharper eyes. By observing distant galaxies and the stars inside them in infrared light, Webb helps astronomers refine distance measurements. Teams working with NASA's Jet Propulsion Laboratory and the European Southern Observatory have been using Webb data to double-check the brightness of certain types of stars that act like cosmic mile markers. Early results suggest the discrepancy isn't going away. If anything, the tension looks real. That means our basic picture of how the universe expands might be missing something. Some scientists think this points to new physics. Maybe dark energy, the mysterious force pushing the universe apart, changes over time. Or maybe there's a hidden type of particle or energy we haven't discovered yet that tweaks how space itself stretches. The Vera Rubin Observatory, once fully online, will map billions of galaxies and track how they move, giving even more clues about whether dark energy behaves the same everywhere and every when. Webb is also changing how we think about the very first stars. These so-called population 3 stars were supposed to be simple, massive, and short-lived, made only of hydrogen and helium. We've never seen one directly, but Webb is catching hints of their fingerprints in early galaxies. Certain chemical patterns in the light from these ancient systems look like what you'd expect if huge, metal-free stars lived and died there. That means the universe may have gone through a wild, fast-burning phase early on, lighting up the darkness much sooner than we thought. And here's the part that quietly shakes a lot of assumptions. Some of the early galaxies Webb sees are surprisingly calm. Not all of them look like stormy wrecks of merging pieces. A few appear almost serene, with steady star formation and less chaos than expected. It suggests the early universe wasn't one single mood. It was a mix of violent fireworks and quiet growth happening side by side. Put all this together and a pattern starts to form. Webb isn't just giving us new pictures. It's telling us our old story of the universe might be too simple. The early cosmos was faster, richer, dustier, and more organized in places than our textbooks prepared us for. And if our models of the beginning are off, that means our guesses about how the universe will end might also need a rewrite. Another door, Webb has kicked open leads straight into one of the strangest topics in modern science: what the universe is actually made of. When we look at galaxies, clusters of galaxies, and the way light bends around massive objects, most of the gravity we measure doesn't come from stars, gas, or dust. It comes from something we can't see at all. We call it dark matter, but that's just a name for our ignorance. We know it's there because galaxies spin too fast to hold together with visible matter alone, and because galaxy clusters act like giant lenses that bend background light in ways only extra mass can explain. Observations from the Hubble spectrograph laid much of this groundwork years ago. Webb is now sharpening the picture. By peering through thick dust and into the hearts of young galaxies, Webb lets astronomers map where stars form and where mass seems to be hiding. Teams at the Harvard-Smithsonian Center for Astrophysics and Keck Observatory in Hawaii are comparing Webb's infrared views with older Hubble data to see how dark matter is distributed in the earliest galaxies. What they're finding is odd. In some young galaxies, the stars seem more tightly packed toward the center than expected, while the surrounding dark matter halos look less dominant than our models predict. That could mean dark matter behaves differently in the early universe, or that the way normal matter clumps together changes how we infer dark matter's presence. Then there's dark energy, the even stranger force, thought to be pushing the universe apart faster and faster. We don't see it, we don't touch it. We only infer it from how galaxies move away from each other over time. Webb's deep field surveys, combined with distance measurements refined by NASA's Jet Propulsion Laboratory teams, are helping astronomers track how the expansion rate may have changed across cosmic history. Early hints suggest the expansion might not be smooth and steady. It could have gone through phases, like a car that speeds up, slows down, then speeds up again. If that's true, our simplest models of dark energy might be wrong. And here's where it gets even more unsettling. Some researchers are exploring whether dark matter and dark energy could be connected two sides of a deeper, unknown piece of physics. Webb can't see these invisible components directly, but by showing us where normal matter is and how galaxies evolve over time, it helps narrow down the possibilities. Every new data point is like shining a flashlight into a dark room and realizing the furniture isn't where you thought it was. At the same time, Webb is giving us better views of black holes in the early universe. We're finding supermassive black holes that already weigh millions or even billions of times more than our sun when the universe was still young. That's a problem, because growing a black hole that big should take a long time. Teams working with data from the European Southern Observatory and the James Webb Space Telescope are seeing signs that some black holes may have formed from the direct collapse of huge gas clouds, skipping the slow growth stage entirely. If true, it means black holes could be born big, not just grow big. All this feeds into one uncomfortable idea. The universe seems to have been very good at building complex structures very quickly. Galaxies, stars, dust, black holes, and the invisible scaffolding of dark matter all came together faster and in more varied ways than we expected. It's like discovering a city with highways, skyscrapers, and power grids already in place when you thought the land was still supposed to be empty fields. Every atom in your body was forged in stars. That sounds poetic, but it's literal. The carbon in your cells, the oxygen in your lungs, the iron in your blood were all made in the hearts of stars that lived and died long before our sun was born. The first stars were huge, short-lived monsters. When they exploded, they seeded space with heavy elements. Over time, those elements gathered into new stars, new planets, and eventually us. This idea isn't new. Astronomers at institutions like the Harvard-Smithsonian Center for Astrophysics in Stanford have talked about stellar nucleosynthesis for decades. What Webb is doing now is showing us this process in action in galaxies so far away that their light left when the universe was still young. Webb can see through thick clouds of dust where new stars and planets are forming right now. In regions like the Carina Nebula, its infrared eyes reveal swirling gas, glowing knots of heat, and baby stars wrapped in cocoons. These aren't just pretty pictures. They're snapshots of the same process that built our solar system about 4.6 billion years ago. By comparing these newborn systems to older ones, scientists at NASA's Jet Propulsion Laboratory are piecing together how common planet formation really is. The early results suggest planets may form quickly and often, even around stars that are still settling down. That raises a wild thought. If planets form easily, then worlds like ours might not be rare at all. And Webb isn't just seeing planets being born, it's starting to taste their atmospheres. When a planet passes in front of its star, some of the starlight filters through the planet's air. Webb's instruments can break that light into a spectrum, revealing the chemicals present. Teams using data alongside the Keck Observatory in Hawaii have already spotted water vapor, carbon dioxide, and hints of methane in the atmospheres of distant exoplanets. None of this proves life, but it proves that the building blocks of life are common. The same simple chemicals that kick-started biology on Earth are floating around in the skies of worlds dozens or hundreds of light years away. Here's the uncomfortable part. If the ingredients for life are everywhere, then the universe might be full of potential habitats. That doesn't mean aliens are waving at us from every planet, but it does mean Earth isn't special in the way we once thought. We're not living on a one-of-a-kind oasis in a cosmic desert. We might be one of countless puddles in a vast, wet landscape. This forces scientists to rethink the old question. If life could be common, why haven't we seen clear signs of it yet? The so-called Fermi paradox still hangs over astronomy. Webb isn't built to spot little green men, but by showing how many planets could host water and organic molecules, it's quietly turning up the pressure on that question. If the universe is good at making habitable worlds, then either life is rare for reasons we don't understand yet, or it's out there and we just haven't learned how to see it clearly. Let's take this one step further, because the question isn't just, are there other worlds out there? But how many chances does the universe get to roll the dice on life? When astronomers at the European Southern Observatory and the Vera C. Rubin Observatory talk about the night sky, they often remind us that what we see is only a thin slice of what exists. Most stars in our galaxy are small, cool red dwarfs. These stars live for trillions of years, far longer than our sun ever will. That gives any planets around them an absurd amount of time to try, fail, and try again at making life. Webb has already looked at several rocky worlds around red dwarfs and found atmospheres where heat could allow liquid water to exist. Some of these planets orbit so close to their stars that a year there lasts only a few days, yet the star itself barely changes for billions of years. Time is the one thing life seems to need more than anything else. Red dwarfs offer oceans of it, but time cuts both ways. Many red dwarfs are violent when they're young, blasting nearby planets with flares that can strip atmospheres and fry surfaces. Scientists at NASA JPL and the Harvard-Smithsonian Center for Astrophysics are still debating whether life could survive that rough childhood. Webb is helping by watching how these atmospheres change over time. Some seem to rebuild. That means even harsh worlds might recover, like a forest growing back after a fire. It's not comforting. It's hopeful in a quiet, stubborn way. Now zoom out even more. Webb is also showing us how galaxies grow and merge. When galaxies crash into each other, gas clouds compress, stars form in bursts, and heavy elements spread across vast regions of space. Over billions of years, this process makes later generations of stars richer in the stuff life needs. Our sun is a third-generation star, built from the ashes of older stars. In other words, the universe had to practice for a long time before it could make planets like Earth. Webb's images of ancient galaxies tell us that this practice started earlier than we thought. That means habitable worlds might have been possible long before Earth even existed. Here's where it gets personal again. Every time Webb pushes the edge of what we can see, it also pushes the edge of how small we feel. You're sitting on a planet orbiting a very average star in one spiral arm of one galaxy among hundreds of billions of galaxies. That can feel pointless at first, but flip it around. In a universe this big, the fact that you're here at all is wild. The odds that stardust would arrange itself into a brain capable of asking these questions are tiny. And yet, here you are, watching light that left distant galaxies billions of years ago and trying to make sense of it. That's the quiet miracle Webb keeps pointing at. Not aliens, not cosmic doom. The simple, strange fact that the universe makes places where thinking beings can exist and wonder about the universe that made them. For years, the James Webb Space Telescope was supposed to give us clearer pictures of stars and planets. That was the safe promise. But what it has really done is crack open the story we thought we understood about how the universe grew up. When teams at NASA's Jet Propulsion Laboratory and the European Southern Observatory compared Webb's deep field images with older Hubble spectrograph records, they realized the early universe wasn't slow and gentle the way our models predicted. It was fast, messy, and shockingly efficient at building huge galaxies in almost no time. Galaxies that, according to our old math, shouldn't even exist yet were already packed with stars and heavy element. That means the universe was making the raw materials for planets, oceans, and chemistry far earlier than we ever believed. Then came the moment that made a lot of astronomers go quiet. Webb's infrared data showed signatures of complex molecules in places where we expected only simple gas. Researchers at the Harvard-Smithsonian Center for Astrophysics and Keck Observatory double-checked the numbers. They ran the models again. Same result. The building blocks of chemistry were showing up earlier and in more places than our textbooks allow. It doesn't mean life found. It means the universe set the table for life way sooner than we thought. The kind of shift that forces scientists to rewrite timelines, rethink how fast stars lived and died, and question how rare worlds like ours really are. When you put all of this together with what Vera Rubin Observatory is mapping about dark matter scaffolding galaxies, and what Arecibo legacy data taught us about strange signals in the sky, a pattern starts to form. The universe isn't just bigger than we imagined. It's more creative. It finds ways to build structure, chemistry, and potential habitats faster and more often than our neat equations allow. Webb didn't break the universe. It exposed how small our old guesses were. And that's uncomfortable because it means we don't sit at the center of a slow, quiet story. We live inside a loud, busy cosmos that has been experimenting with worlds long before Earth showed up to the party. So here's the real takeaway. Webb didn't just look too deep into space. It looked too deep into our assumptions. The early universe wasn't empty. It wasn't patient. It was already busy building the ingredients for complexity. That doesn't make our place in the cosmos smaller. It makes it more honest. We're not special because we're alone. We're special because we exist at all in a universe that clearly loves to make complicated things and then watch them try to understand where they came from. If this blew your mind even a little, don't stop here. Tap the next video on your screen and follow this story as Webb keeps peeling back the layers of the universe.